This video is on going from standard form to vertex form. This process is also known as completing the square, which is what we're going to see why that's the case, or why it's named that, in just a minute when we go through some examples. Now, the reason that we want to do this is because, as we've seen in one of the other previous videos, is that standard form, which is an equation that looks like this. So x squared plus 4x minus 2. We can't really get a lot of information from that equation. We can find out what the y-intercept is, and we can get the direction of opening, and that's about it. But what we did find was that if we had factored form or vertex form, we could actually get all the information we wanted. And so this is just another method of switching form. So we're going from standard form to vertex form. The same relation that this quadratic equation represents can, in vertex form, it looks like this. And I'm going to prove to you that those are in fact the same, and because I'm going to expand and simplify this one so that you can see it. So y equals, and I have my brackets, and into my chart. So I have x plus 2 times x plus 2, x squared, 2x, 2x, 4. And now I take all of the stuff in here, the expanded part, and I write that out here, again in brackets, plus 2x plus 2x plus 4 minus 6. I'm going to simplify what's in my brackets. X squared plus 4x plus 4. Because out here, all I have is a 1, so that's multiplying 1 into everything in the bracket, so that means which stays the same, so I can get rid of the brackets. X squared plus 4x plus 4 minus 6, and simplifying it again, you can see that this and this are the same. These two equations are the same, so that means that this equation and this equation represent the same quadratic relation. And so what our goal is here is to go from this form to this form. And what we're essentially going to be doing is working back. That's it. So just like with factoring, if you've looked at the factoring videos, where we just worked from this form backwards, and that's what we're going to do. Alright, so let's start with an example. So we have y equals x squared plus 4x minus 3. And in this example, what I'm going to do is I'm going to go back a little bit. In all my other previous videos, I haven't really talked a lot about algebra tiles, but in this case I think it's really important because it really shows why we're doing what we're doing. And it's also the basis from where our chart is built off of. And so I think this will help conceptually for you to understand what it is that we're doing. So if I wanted to represent this using algebra tiles, it would look like this. And I'll explain what the tiles mean in just a moment. And let's pretend that these four are identical and in size and shape. They're supposed to be rectangles. And let's pretend that these four are perfect squares. And they're smaller than this square here. So how this works is that I'm going to start with these tiles here. Most algebra tile sets, they will have all algebra tile sets will have two different colors, one to represent positive and one to represent negative. I use red for positive and blue for negative, and I think of it as temperature. So hot being, red being hot above 0, and blue being cold, so below 0. Other people do it using banking methods, so the reverse, so being in the red and being in the black. But I use the red as positive and blue as negative. When we look here and pretending that these are perfect squares, we would assign the length of this to be 1 and the width of this to be 1. So when we think of area model, we would have 1 times 1. And so each of these would be 1, but because they're blue, they're -1. So I have -1, -1, and -1. So those are all -1, which is how we get our -3. For these ones, and pretending I had done these perfectly again, this length here, or sorry, the width here, which is 1, would fit up against this tile here. So we know the width here is 1. Our length of this is actually unknown. And because our length is unknown, we usually assign that a variable, and we're going to assign it x. So we would have a width of 1 and a length of x, and so that means area model x times 1 is x. So I have x, 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 and x. So I now have my 4x. So these all represent 4x. And I will write -3 beside these guys. Then, with this one here, if I was able to take my, and these were done perfectly, my length here would be the exact length of this here and also the same as the width. So I'd have x times x, which gives me x squared. That's not a very good square. There we go. So this is how we have x squared plus 4x minus 3. So what I'm going to do now is I'm going to rearrange these tiles so that they all fit together. We're going to try and fit all of them together to make a perfect square. Now, one thing to keep in mind about algebra tiles is that if you usually have them on your desk, you know that you have a set of them. So I always call the ones that you're not using at the time the bank, because you can always borrow tiles from the bank, but the only principle is that whatever you borrow, so say you borrow a positive unit tile, you have to borrow a negative unit tile, and that's so that you can keep the original equation the same, because that's the 0 principle. -1 plus 1 gives you 0. Now, when setting these up, we actually start with our chart. So there's our chart. And what we end up doing is that we have to place the tiles so they fill up this area here. So if you remember when we were expanding and simplifying, what was in here was really what was ended up being our standard form. So that's all what goes in here. And what's on the outside is what our factors are. And so since we're starting with standard form, we're actually going to place these tiles in here. One of the other things that we knew when we were using the chart was that x squared, our x squareds always go in this top part, our x's go here, and then our units go in here. And so we're going to follow that same principle. So I'm going to redraw these. One of the things that when we're going through this process of completing the square is that we always kind of ignore our unit tiles until the very end. Because what our goal here is that we're going to actually try to make a perfect square so that our length and our width are the same. So I'm going to redraw these. I have my x squared here. And because I'm trying to make a perfect square where my length and width are the same, that means I'm going to have to evenly distribute my x tiles here and here in order for it to be a perfect square. So again, my drawing isn't perfect, so you are going to forgive me. So I'll have 2 x's here and 2 x's here. So using that same principle with our, as we did with the chart, we know that we are multiplying rows and columns together. So we know that this times this will give us what's in here. This times this will give us what's in here, and this times this gives us here, and this times this gives us what's in here. But if I look at this logically, how many unit tiles, because that's what's going to end up in here, do we need to fill in this so we have a perfect square? Well, since these are all positives, we know we need to have 4 positive tiles. And really all we have is these negative tiles, so we can't really work with those. I'm actually going to draw those in because I haven't done that yet. So here's my 3 negative ones. And we can't use those in order to fill what's in this area here. We need to have 4 positives. So this is where I'm going to borrow from the bank. I'm going to borrow 4 positive tiles to fill in here. So 1, 2, 3, 4. But now I've changed my equation, because now I have x squared plus 4x plus 4 minus 3. So that gives me x squared plus 4x plus 1. And that's now changed. So whenever we're borrowing, so I borrowed 4 positives. In order to keep this the same, I actually have to borrow 4 negatives. So I'm going to borrow 4 negatives from the bank, and I'm going to keep them over here because they came along for the ride with these guys. So I have my 4 negatives. Now I have to ask myself, well, did I make a perfect square in this chart? Well, yes, I have. Okay, so now what we're going to do is, as with factoring, we're actually going to factor our chart. We're going to factor everything. So here I have x, and this is plus 2. This is x plus 2. So those are my 2 factors. Then what I'm going to do is I'm going to take these units and these units, and I'm going to join them up. So now, if I'm writing this all out, I have y equals x plus 2 times x plus 2, and adding those up I have minus 7. And you can't really see that, so I'm going to erase that and make it neater. So y equals x plus 2 times x plus 2 minus 7. All right, now, because these two are identical, x plus 2 times x plus 2, I can write that as x plus 2 all squared minus 7. So that is, using algebra tiles, how we go from standard form to vertex form. And that's because we're making a perfect square. That's why this process is called completing the square. You are completing a square using, well, I'm going to call it tiles, because you're borrowing tiles from the bank to make a perfect square. And if I expanded this out, I would get the exact same as we have here. So what I'm going to do on the next slide is I'm actually going to go through the same process of taking this, but not necessarily using the tiles, so you can see how it looks like with the chart. Okay, so again, starting with this example, what we're going to do is we are going to group our x squared and our x's together. And the reason that we're doing that is because it's only these two that go into the chart. the unit tiles, we just kind of leave those off to the side. We don't care about those until the very end. And you can also think about that when you look at vertex form. The units are just kind of, it's almost like they're an afterthought. They're the things that are just off to the side. So even in the equation. So we just have to think of it the same way. Alrighty, so now we're going to make our chart. It's not very nice. There we go. And again, we have our -3. So as with our chart, we know that the x squared term is going to go here, and the x's have to go here and here. So x squared here. Now, our x's, because we want to make a perfect square, our length and width have to be the same, so we have to divide those up equally into here and here. So 4x divided by 2 is 2x, and 2x. And now I have to fill in this here. I know that to make that perfect, it's got to be 4 to fill in the gap here. I'm going to borrow 4 from the bank. Now, if I'm borrowing 4 positive unit tiles from the bank, I also have to borrow 4 negative tiles. It's the only way it's going to work. So now what I'm going to do is factor. So I factor each column, common factor, and each row. So I have x, and I have 2, x, and 2. So I now have my factors. And what I'm also going to do is I'm going to bring my units out here. So we take our -4 out of the brackets. Now I'm going to rewrite this. So I have my factors of x plus 2 times x plus 2. And I have -4 minus 3. And because these two are identical, it's x plus 2 all squared minus 7. So now we've gone from standard form to vertex form. And what's nice is that I can immediately get the vertex from this form of the equation. So I'm able to answer some questions right away based on if they're asking for the vertex. So what I'm going to do now is I'm going to go through another example, and then I'm going to let you try a couple on your own. And I know this video takes a little bit to go through, but it's just I want to make sure that you've seen enough examples and know where this is coming from in order to be able to do it properly. All right, so here's our next example, x squared minus 6x plus 5. So again, going through the process, we're going to group our x squared and our x's together and leave the units all by themselves. Now we are going to put our x squared and our x's into our chart to make a perfect square. So keeping in mind our x squared goes here. Then I need to put my negative 6x evenly distributed here and here. So cutting negative 6x in half, I have negative 3x and negative 3x. And in order to finish this off, I have to, finish off the chart. I have -3 times -3, which will give me 9. I have to borrow 9 from the bank. If I'm borrowing 9 from the bank, I also have to borrow -9. So now I'm going to factor my rows and columns. So I have x minus 3 and x minus 3. Then what I'm going to do is I'm going to bring that out this way to show that I'm taking my unit tiles and I'm joining them up with the 5. So I have y equals x minus 3 times x minus 3 minus 9 plus 5, which is x minus 3 all squared minus 4. All right, so we've seen this. We've seen another example. I'm going to put another example on the next slide, and I'd like you guys to try that one. All right, so I'd like you to try x squared plus 2x plus 15. I want you to change that to vertex form by completing the square. Okay, so I hope you have now tried to do this one. And one thing I encourage you is please make sure you try these because, as I mentioned in class many times, you should get good at doing the math yourself and not get really good at watching people do math. There's a difference in terms of whether or not you can do it. So here we go in order to check your work. So again, I'm going to group my x squared and my x's together. I'll leave the units off to the side because we don't care about those till the end. Make the chart. We know that x squared goes here. Then I have to, in order to make a perfect square, same length, same width, I'm going to cut that in half. So I have x there and x there. What gets filled in here is really what these two multiply to. So I'm going to borrow 1 from the bank. If I borrow 1 from the bank, I also have to borrow -1 to make things all still the same. So I've done that. Now I'm going to factor out my rows and columns. So I have x plus 1, x plus 1. I join those two together and I write this out. So I have x plus 1 times x plus 1. And then I have plus 15 minus 1. And because x plus 1 times x plus 1 is really x plus 1 squared, and plus 14. There we go. So that is y equals x squared plus 2x plus 15 is y equals x plus 1 all squared plus 14 in vertex form. So with the last few examples, what has been, you may have noticed this, but our a value, or our value out here, our number out here has been a 1. So what we need to do now is look at what happens when our a value isn't 1. Because our process changes slightly. Not very much though, just slightly. All right, so I have y equals 2x squared plus 12x plus 21. And we are going to change this to vertex form by completing the square. One thing when we are grouping our, so I'll start the process actually. So we have where we're going to group our x squareds. And our x's together. So that doesn't change. The only thing that looks slightly different is the fact that we have a 2 here and not a 1. Well, what this means is this 2, or whatever coefficient is in front of the x squared term, actually describes how many perfect squares we're creating. So in this case, we're actually creating 2 perfect squares. Well, if they're perfect squares and they're identical to each other, we really only want to do that once. And so what we're going to do is we're going to common factor out the 2 from these 2 terms, because why would we do something twice that's identical? We would only do it once because that would be more efficient. So what we're going to do is I'm common factoring out the 2 from the x squared and the x term. I am not, and I'm repeating this again, I am not common factoring it from the units because we don't care about the units until the very end. We don't use these when we're completing our square, so we don't care about them. We're not going to common factor from this one. We are only common factoring from these 2. All right, so that gives me x squared plus 6x, and see again, I have my 21 on the outside of the brackets. Alrighty, so now I'm going to take this stuff here and fill in my chart. So there's my chart. So I have my x squared here, and I know that in order to make a perfect square, I have to have the same length and width, so these x's have to be evenly distributed in these two areas of the chart. So I have 3x and 3x. In order to fill in the bottom right, I need to borrow 9 because that will fill in my chart. So I'm borrowing 9, but I am also borrowing -9 in order to keep it the same. So it's the same equation. Now I'm going to common factor out the rows and columns. So I have x plus 3 and x plus 3. Now, when I'm joining up my units, what we have to do is we have to be very careful. So I am pulling out the -9. But when we think about this, we have our 2 out here. Because this is telling us that we are multiplying 2 times everything in the brackets. Well, this -9 is part of the brackets. This stuff in here is what we are using to create one square, but in fact we're doing 2 identical squares. So what we need to do is multiply this by 2, and that gives us -18. And it's these two that we're going to end up joining up together. Alrighty, so we have y equals 2 times x plus 3 times x plus 3 plus 21 minus 18. And I have y equals 2. And we have x plus 3, which is identical to each other, multiplied, gives us squared. And the difference between 21 and 18 is 3. So we have y equals 2, x plus 3 all squared, plus 3. Okay, so one more example. Y equals -3x squared plus 12x plus 17. We're going to put that into vertex form. So again, we are grouping our x squareds and our x's together because we don't care about the units until the very end. Now, this time I have -3 as my a value, and I'm going to common factor that out. So I have -3 x squared minus 4x plus 17. So again, I have only common factored that out from these two terms. I am not, and I repeat, I am not common factoring that from the 17. We don't care about the 17 until the very end. So we do not common factor that out from the constant term. Alrighty, so now I'm going to put all of that into my chart. Well, not all of it, just the stuff in the brackets. So I have x squared, and I need to evenly divide these two into those two boxes in the chart. So I have -2x and -2x, and the reason I'm doing that is because we want to have a perfect square, so our length and width are the same. So to fill in our bottom right-hand box, we need to have 4, because if I have -2 and -2 here, to fill this in, I have space for 4. If I'm borrowing 4 from the bank, then I also need to borrow -4. And this -4 is within the brackets. Okay, common factoring our rows and columns. I have x minus 2 and x minus 2. Now, when I bring my 4 units out, we have to remember that we don't just have -4, we actually have -4 times the -3. So I'm going to multiply that by -3, and I get 12, positive 12. So that gives me -3 times x minus 2 times x minus 2 plus 17 plus 12. And y equals -3, x minus 2 all squared, plus 29. Now, some students ask me, well, do I have to write out this step here? I'm not saying you do, but it's nice to see because going directly from here to here, students make mistakes. So please keep that in mind. This is just a way of organizing all of what you have here, because you actually did a whole bunch of steps here. And this is just organizing those before we get to the final answer. I'm not saying you have to do it, but sometimes, especially at first, it's the baby steps, and making sure that you show your work. And this is where you may catch mistakes that you may make. So please actually write out this step for just when you're starting, you know, until you get really confident with what it is you're doing. So this is one I'd like you to try on your own. Y equals minus 5x squared minus 40x minus 25. So please pause the video and get good at doing math on your own instead of watching somebody else do math. Okay, so let's take this up. I'm going to group my x squareds and my x's together. Keep the units off to the side because we don't care about them till the very end. I'm going to common factor out the negative 5 from only what's in the brackets. So x squared, and that is 8x. And then I'm going to put everything in the brackets into my chart. I am going to mention this right now. Sorry, backtracking a bit. When I common factor out the minus 5, I'm left with x squared. Minus 40x divided by minus 5 gives me 8x. If you're wondering why that changed sign, it's because I'm common factoring out the negative 5. Okay, so into my chart. I have x squared. I have to evenly divide up my 8x into these two so I can have a perfect square, a perfect length and a perfect width that are identical. Sorry, I don't mean perfect because there really isn't a perfect length and width, but that our length and width are identical in order to make a perfect square. So I have 4x here and 4x here. In order to fill in this here, I'll have a space for 16 because 4 times 4 is 16. So 16 will fit in there, 16 units. Because I have to borrow 16 units from the bank, I'm also going to borrow minus 16 units from the bank. Common factoring, I have x and 4, x and 4. The minus 16 comes out of the brackets, but we have to remember that we have to multiply that by minus 5. So times minus 5, and that will give me, so that'll give me minus 16 times minus 5 is 64 is 80. So I have positive 80. Y equals, writing this out, oh, I forgot my minus 5. Minus 5 times x plus 4 times x plus 4 plus 80 minus 25, and that gives me minus 5 times x plus 4 all squared, and that is plus 55. There we go. So we have our equations in vertex form. So now we have to think of, well, why the heck, and I said this at the beginning, why am I doing this? Why am I going through this process of changing from standard form to vertex form in this case? Well, it's because, again, we can't get all of the information that we would like from standard form. And so what's nice is that I've gone to vertex form, and so now what I can do is find out information from this form of the equation. And the reason I would go to this form over factored form is if I'm actually looking directly for the vertex. And the vertex in this case, so don't forget that here we have the x coordinate of the vertex, but we changed the sign. And here we have the y coordinate of the vertex. So the vertex in this case is -4, 55. So we're able to determine the vertex directly from this form. And sometimes you'll get into questions where it will say, what's the vertex, or what's the maximum, or what's the minimum? You can find that directly from vertex form. All right, so this part here really is, or this part of the video is where all I want to do is go through the process of completing the square and then actually finding the properties of the quadratic relation that we're dealing with. Let's just go through this. So I have y equals 4x squared minus 24x minus 50. And again, using this form of the equation, we can really only find out one piece of information, well, two pieces of information, and that is the direction of opening and the y-intercept. So the direction of opening, so that's the DOO, direction of opening. We know that it opens up, and that is because our A value is positive, plus VE is positive. So our A value is 4. It's positive, so it opens up. Our y-intercept, that is when x is equal to 0. So I have 4 times 0 squared minus 24 times 0 minus 50. So I have 0 minus 0 minus 50 is minus 50. So our y-intercept is 0 minus 50. So then it comes to the rest. So the x-intercepts, the x-intercepts, the vertex, the axis of symmetry, the maximum or the minimum value, we need to determine that, and or those pieces of information or those properties, but we can't really do that from this form. So I'm going to actually change to vertex form. So going through my process, I'm grouping together my first two terms, leaving my units off to the side, common factoring out the 4 from our terms, only these two, because those are the only two that matter with the chart. So I have x squared minus 6x minus 50. I'm going to put this into the chart, so I have my 4. So x squared goes here. Then I have to evenly distribute the x's into these two, so I can have a perfect square. So I have minus 3 and minus 3. To fill in the bottom right-hand corner, I will need to borrow 9 from the bank, because minus 3 times minus 3 is 9. If I am borrowing 9 from the bank, then I also have to borrow minus 9. Factoring out my rows and columns, I have x minus 3, x minus 3. Then I have to join my units up, my units that are left by themselves, join them up with the other units. Not forgetting that I have my 4 out here. So I have to multiply my minus 9 by 4, which will give me minus 36. So, writing that all out, I'm going to come up here. So I have y equals 4 times x minus 3 times x minus 3 and that is minus 86. This is what happens when you make something up on the fly. So minus 86, and I have y equals 4 times x minus 3 all squared minus 86. And so now, pardon me, I can determine what the vertex is. So my vertex is, this is the x coordinate of the vertex, but you change your sign, and this is the y coordinate of the vertex. So I have the vertex is 3 minus 86. So my vertex, what's nice about that is I can actually figure out what my axis of symmetry is, my equation for my axis of symmetry, and what my maximum or minimum value is. So my axis of symmetry is the x coordinate of the vertex, which is the 3, so that's x equals 3. And my maximum or minimum will be my y coordinate of the vertex, because that will either be the highest y value or the lowest y value, depending on what direction it opens. In this case, our parabola, our graph, will open up, and so that means that we will have a minimum. And so if we look here, the minimum is at minus 86. So we have a minimum, and that's y equals minus 86. So it's the y coordinate of the vertex. So we have our direction of opening, our y-intercept, our vertex, our axis of symmetry, our minimum value. The last thing we need are the x-intercepts. And so I'm just going to flip to the next slide, and we will determine what those are. Okay, so we want to find the x-intercepts. And this is when y is equal to 0. So I set my equation to 0, and I have 4 times x minus 3 all squared minus 86. And what I'm going to do is, because I have an equation with one unknown, which is my x, I'm just going to rearrange this and isolate for x. So we're going to add 86 to both sides to get rid of the 86. So I have 86 equals 4 times x minus 3 all squared. My next step is to divide everything by 4. Pardon me. So I have 86 divided by 4 is equal to x minus 3 all squared. So in order to get rid of something, I do the opposite operation. So because I was multiplying by 4, I'm now dividing by 4. This becomes 21.5. Now I have to get rid of the square. So the opposite of squaring something is taking the square root. And as mentioned in one of the previous videos, we actually have two possible square roots. We have a positive square root and a negative square root. Right? Because negative 2 times negative 2 would be 4, and 2 times 2 is 4. So you actually always have a positive and a negative square root. Our calculators just don't tell us that. So this means we have two possible branches, and I'm actually going to bring those branches up here. So I'm going to rewrite this so that we can see it better. So plus or minus the root of 21.5 is x minus 3. So one branch will have the negative root of 21.5. On the other branch, I'll have the positive root of 21.5 equals x minus 3. So there's two ways that you can, so now solving, and I'm going to show there's two ways of writing this. So because 21.5 does not have a perfect square root, and that's fine because life isn't perfect all the time. So if I was going to isolate for x here, I would have to add 3 to both sides. So I would have 3, because that's plus 3, minus the root of 21.5 equals x. On this side, again, I'm going to add 3 to both sides, so I'd have 3 plus the root of 21.5 equals x. So those would be our two possible roots, or x-intercepts. So 3 minus the root of 21.5 or 3 plus the root of 21.5. And if you wanted to have an exact answer, you could leave it that way. Or if you actually had to answer like time or something like this, or you know, where we're dealing with a real world situation, we can take the square root of 21.5, which, and I've just calculated that, it's 4.64, and that's to 2 decimal places. So I have 3 minus 4.64 equals x, or 3 plus 4.64 equals x. And so that gives me either negative 1.64 or I have 7.64. All right, so I'd like you to try this one. I'd like you to determine all of the properties of this particular quadratic relation. So y equals minus 2x squared plus 20x minus 60. So please pause the video and try this on your own, and you can start the video if either A, you get into trouble, or B, if you just want to check the answers. Alrighty, so what I'm going to do with this one is I'm going to start by actually going right to vertex form and then looking at how to get the properties, all of the properties from vertex form. So I am going to group my x squared and my x's together. My units off to the side. Common factor out the -2 from the information in the bracket, so from the terms in the bracket. So I have minus 2, and I'm left with x squared minus 10x minus 60. And so again, common factoring, -2x squared divided by -2 leaves me with x squared, and positive 20x divided by -2 leaves me with negative 10x. And I again ignored the minus 60. Not common factoring from there. So, putting everything into the chart. So I have x squared here, and I have to evenly divide the negative 10x into these two boxes. So I have minus 5x and minus 5x in order to create a perfect square, same length, same width. Then I'm going to fill in this box here, and I will need to borrow 25 to do that. So if I'm borrowing positive 25, I also have to borrow minus 25. Now I'm going to common factor. I have x here and minus 5, x minus 5. So next thing, I'm going to bring those out. So, but again, because I am multiplying everything in the brackets by minus 2, when I bring this out of the brackets, I have to also multiply by minus 2. And that will give me positive 50. So writing this out, I have minus 2 x minus 5 times x minus 5. And then I'm adding 50 and subtracting 60. So that will give me minus 2 x minus 5 all squared minus 10. So that is our equation in vertex form. So what I'm going to do is I'm going to rewrite that on the next slide. Oh, actually, we can get some information that I have space to write on here. So I will do that. So let's look at what information I can get from here. So I'm just going to do a line here. Okay, so in terms of our properties, we can look at our direction of opening. Direction of opening, Because our A value is negative, that means it's sad, and so it opens down. So down, and that's because A is less than 0, really. So it's negative, so it opens down. We can get our vertex. And our vertex is x-coordinate, y-coordinate, but our x-coordinate, we change the sign. So our vertex is 5, -10. From our vertex, we can get two pieces of information. We can get our axis of symmetry, so AOS. That's always the x-coordinate of the vertex, so that's x equals 5. And we can also get our maximum or minimum. So in this case, because it opens down, that means our vertex will be the highest point, so that's a maximum. So our maximum is y equals -10. I must have made a mistake here. No, I didn't. Sorry, I was just thinking there. So yeah, so our maximum value is -10. All right, so last two things we need to find are our Y-intercept and our X-intercept, and I'm going to do that on the next slide. All right, so let's find the Y-intercept. And this is when x is equal to 0, so I'm going to substitute in 0 for x. And that gives me -5 all squared minus 10. And I have -2 times 25 minus 10. So I have -50 minus 10. And I have -60. So y is equal to -60. So that is our Y-intercept. Now let's try and find the X-intercepts. Okay, so X-intercepts, I'm just going to draw a line here to differentiate between the two sides. So this is the X-intercepts, and this is when y is equal to 0. So I'm going to set my equation to 0. X minus 5 all squared minus 10. And I'm going to try and solve this. So I'm going to add 10 to both sides. So I have 10 equals -2. X minus 5 all squared. Now I'm going to divide both sides by -2. So I have 10 divided by -2 equals x minus 5 all squared. So that gives me -5 is x minus 5 all squared. Now I have to take the square root of both sides, and this is where you should actually go, something doesn't quite make sense here. Because I cannot take the square root of a negative number. You cannot do this. There are not two numbers that multiply by themselves to give you a negative number, so we can't do this. So when you're running into a situation like this, you should stop and think, well, there are situations where you can actually have a graph where there are no x-intercepts. So this particular relation that we've got here doesn't actually ever cross the x-axis, and we can actually think about this logically. We know that the vertex is, I'm just going to do a quick sketch here, I'm using red, is at 5, -10. So 5, -10, which would be somewhere, let's pretend down here. So that actually isn't a very good graph at all, and I'm going to redo that because to make more sense. Okay, so I'm going to do this. So we have 5, -10, which would be, I don't know, we're going to go there. So this is 5, -10, and it opens down. So our graph will actually go like this, which means that it actually doesn't have any x-intercepts. So thinking, so this is x, this is y, if we look at this sketch, it would make sense. We actually have no x-intercepts. And so one way to actually, before you even start solving, if you're in vertex form, you can say, oh, well, if I look at my equation, I open down, and then my maximum value is below the y-axis. Therefore, there won't be any x-intercepts. So we would actually expect this. So we have no x-intercepts, and that happens. We can have a relation that never crosses the x-axis. So that was a little bit of an interesting one to throw in there, but it's just something for you to recognize that in this particular case, we'd actually have no factored form because we would have no x-intercepts. Alrighty, so there's your kind of recap on how to complete the square and really what the purpose of it is. And so happy practicing with the other problems that you may have been assigned.